As we begin, in this concrete example, we're going to work over some basics of checking and validating the structural beam for its strength and loads applied to it. This will not be a detailed, complete design of all the aspects of designing a concrete beam. Concrete beam design is an involved process. It can be iterative. And what I'm wanting to show today are just some basic concepts while you're working with a structural analysis application, some quick rules of thumb to check as you go. Formal concrete beam designs would be shown in your concrete engineering textbooks. What I'm going to do quickly though is sketch our concrete beam. In the example, it's 30 feet. And if I use an 1/8 inch scale and I look across here, I come out to 30 feet, being right there. And what I'm going to simply put in here, this is using the graph paper we showed how to create. And so this is to scale at 1/8 inch scale, 30-foot beam. And we said in our example that our ultimate load on the member was 3 kips per foot. And then what that would coincide with is a shear diagram that we would pick up. Again, if we're working on the document here, shear for the member design could be D away from the supports. Right now I'm just going to work off centerline numbers for a quick estimate. I'm going to come up with 45 kips. And that is at center line. I'm going to note that with a center line. That's also the beam reaction, which we saw in the software. And then D away from the support, we could back off with the load and come up with a reduced VU at D away from the support. So that's VU at the center line of the support. Our moment diagram, we would know intuitively on this member that the moment should be WL squared over 8. It's a simple span beam. And from that, we know the diagram, I'm going to show it positive up, even though most applications would show tension side positive, but for illustration purposes I'm showing it positive side up. MU would be WU L squared over 8. We calculated this earlier on screen. If I take the W squared over 8, we're going to end up with 337.5 kip feet. And in this example, we're going to say, for talking purposes, that our F prime C is 4 KSI, and then our steel in this example is 60 KSI for the yield strength. And if I were just quickly checking a singly reinforced member, in our example we had that the width of this member is 18 inches and that the height of the member is 28 inches. And if I wanted to look at its span over 16, this would be the depth limits. The shallowest member we could have would be 22 inches. So if I did 30 feet times 12 divided by 16, it'd give me 22.5 inches. So that is a ratio that's in the American Concrete Institute code. That's the ACI beam depth ratio. Other building concrete codes will have similar depth of member to span length, and this is to account for deflection considerations. So moving forward, that is H, that is not the D of the member. D is subtracting out the clear cover, and D is from the extreme top compression fiber down to the centroid of the tension of the member. So if I were to come over and in this case, for an example, I'm going to sketch our detail at 3/4 inch scale, and we talked about the member being 28 inches, so come down, that's 2 foot. Don't know what reinforcing I'm going to use yet, but it's down at this level, and often in a sketch we'll just show a block down there to represent it, and then that dimension I'm going to say is approximately 24 inches, and that leaves me 4 inches from the bottom to the centroid of the steel. In the text, we've talked about a approximation number, which would be that the area of steel is equal to the moment in kip feet divided by 4 times the depth in inches. And if I were to work through that number, I would take 337.5, divide by 4, and by 24. And I'm going to come up with a number approximately 3.5 inches squared. This is a quick way to get an early on approximation of the steel quantity. We could also look at another rule of thumb, which would be on the shear stress. If I took my reaction, first let me take and get VU at D over 2 away from the support. So that would be VU, which is 45 kips, minus WU times D over 2. And that would equal 45 kips minus, in this case, D's 24 inches divided by 2 is 1 foot. 1 foot times 3 kips per foot would simply be 3 kips. And so I'm going to really be dealing with an effective shear of 42 kips. And then the stress, little VU, at D over 2, would then be 42 kips divided by B of 18 inches and D of 24 inches. And I'm going to come up with a stress that is about 97.2 psi. From rules of thumb, I already know that this is a very low stress, and it's going to most likely just be minimum steel required. An example when working with this with a stress at that level would be seen in a document such as ACI's Handbook for Concrete Structural Reinforcing Elements. This book's known as SP17, And the parentheses is simply the year it was published. This is a 09 copy. And what I'm going to do here is simply look at the shear guidelines. Now that I've turned back to this table, what I want to point out to in it is that it has concrete strengths across the bottom. We've said that we're going to use 4,000 concrete. And what I would start to look at is no stirrups required, minimum stirrups required, and look at the stresses at that level. So a key point, I'm already seeing that my VU over phi BW, and I'm going to factor out the phi. My loads right now are right around 108 psi. If I were to add the phi in at the bottom, .2. So I'm already going to be really in this range where it's minimum stirrups. I'll go ahead and calculate it. My threshold for minimum stirrups will be 126 psi, so I'm at 129 in my example. So it's really just going to be minimum stirrups required. So this will just be a preliminary pass. I'm trying to find out if our solution is workable geometry wise as we begin to validate the design. So what I'm going to do next is start to look at what this beam design would begin to approach, and from there I'll see if it looks feasible. So I'm going to draw in our width of our member. I'm using 1.5 inch scale for the design here. I'm going to go down 28 inches. Simply put, that's the major line here plus 4. And I know on the sides I'm going to have 1.5 inch clear cover. I'm going to hold it 2 inches off the bottom. This is just a rough hand sketch. And if I were looking at my steel, I said over here in my quick approximation that I'm looking for 3.51 inches of steel. That's starting to look something on the order of 5 number 8 bars, and I'm going to just kind of get a feel if that will even fit. And I think it will. If I started to look at my bar spacing graphically, looking like I can fit those in without too much trouble. Also, another way is to legitimately calculate clear cover plus the diameter of the stirrup on one side, and then your bars, I try to maintain about 2 bar diameter gap is a good rule of thumb for congestion. And so I'm going to show in 5 number 8s. Then again, at the top here, the top is not in tension, but we need at least a bar in each corner for constructability, and that just really holds the ties together. If you wanted, you could have a smaller bar up there and simply put in something like 2 number 6 bars at the top. Stirrups, since it's minimum, I believe number 3 ties will work. I'm going to write verify here. All of these numbers have been developed very quickly with less than a page of rules of thumb. But this is giving us a beam size that we could more formally run through the detailed calculations. This is the kind of work you could do quickly before you've gotten into the detailed calculations that must be done at the end of the day. I'm going to say that's approximately 4 inches there. That concludes this video, which is just a very simple overview of using some of the rules of thumb with concrete design.